Hey everybody, there seemed to be some interest and actually a little bit of confusion about this last week that came up on Slack about this new pattern that we're talking about. I think it was Riley and Hannah both had some questions about the Dable interface and how we were supposed to use that. So I had some time this evening, so I put together some slides and thought I'd just record a quick video introduction onto this panel and or onto this pattern, and maybe clear some things up. So first, a little background. When planning out your software architecture, one of the more challenging aspects is wrapping your head around the many complex ways that the objects in your application can interact. A modern app, is like we work with, can represent a very complex hierarchy of interacting objects, sometimes many levels deep, and you may have had the unpleasant experience of keeping track of the flow of data through the different possible routes in your dependency tree. And you've probably seen this, but with every type or object you add to this tree, the graph complexity increases proportionally to the square of the tree's root diameter. So the Dable pattern is a compound behavioral design pattern that defines an object which encapsulates and mediates all the different interactions between a set of quasi-inherited types. Often a situation arises involving a family of interacting objects which inherit from a base object 2 or more generations removed. Because of the nature of these relationships, these so-called cousin types can manifest expanding entropic behavioral effects, which are difficult for an engineer to manage using traditional means. In the early 1960s, a Sir Francis Dable, I think, a software behaviorism researcher at CERN, addressed the issue by applying a beta reduction transform to the participating entities in a recursive reflection algorithm. He found that making the entities reflect on their position in the greater hierarchy significantly raises their empathic cofactors to such a degree that the entropic decay in the system as a whole could be significantly delayed and even prevented in systems rated at 68 watts or below. So let's look at an example of how all of this might be used. Okay, so let's move to the slides. Imagine we have an object hierarchy involving a fairly deep inheritance structure. For example, let's model out a collection of animal types, all inheriting from a single base type. If you look at these leaf end objects, you can readily see that the likely antagonism between the various types increases with difference from like types, but then begins to diminish, especially once we pass a multiple inheritance boundary. And we can actually chart that, and you can see that a lion is more likely to be antagonistic to a monkey, but once we get past the platypus, which exhibits some multiple inheritance traits, the antagonism begins to decrease. It's not that the lion really particularly loves a tick or an ant, but it's just not really that motivated to antagonize them. Now, to complicate matters, there's actually an asymmetry that arises when a unidirectional symbiosis relationship exists between entities of different types. Some entities might be highly attracted to others that are likely to return the attraction in a highly deconstructive way. Like, ticks really love lions, but lions don't really care that much for ticks. If nothing is done to control the behavioral interactions between these types, you probably will see that normal operation will be possible for a few cycles before a series of non-deterministic runaway events becomes pretty inevitable. It's obviously something you want to avoid. So the naive way to address the compounding effects of this kind of relational distance is for the developer to manually isolate the adversely interacting specimens. This approach works but does not scale very well. As the tree grows, the manpower required to maintain balance increases dramatically, and the last thing you want is for the structure to overwhelm the available engineering resources, as developers safely could be severely compromised. Okay, so let's get back to the Dable pattern. How does the Dable pattern help? Sir Dable's fundamental contribution, and it seems obvious in hindsight, was that the opposite of entropy or chaos is simply logic. So while most architectural patterns encourage the strict separation of business logic from the interaction layers, The Dable pattern manages the behavior of the app by embedding logic in specially designed boundaries between interactors. So let's go back to our example and see what it might look like if we applied the pattern there. The first step is to wrap each entity inside of a special adapter class that implements the Dable interface. Now, at first glance, you might think that says Dable, but that's just an unfortunate quirk of this pattern. Mr. Dable, Sir Dable, I guess, wrote extensively about his search for a less confusing name for this interface, but he ultimately decided that familiarity with the concept and the term would eventually overcome any initial confusion from the name. So he stuck with Dable. Okay, so the next step is to register the adapters, these Dable adapters, with Dable mediator instances that we're showing here with these blue circles. Because of the recursive nature of the reducer used, the process is repeated at larger scales until you reach the Dable Grand Master, which is ultimately responsible for the behavior of all of the objects under its control. Now, with the Dable pattern in place, like we're showing here, each entity is constrained in its behavior to a well-defined logical boundary. If any leakage does occur, which sometimes happens, the Grandmaster is ready and able to negate it using a reaction consistent with Newton's second law. All you have to know is that internally, the Dable pattern uses a combination of lambda and gamma-inspired calculus processes and a simple recombination of the standard gang of 4 behavioral design patterns to convert polyadic molecularized object divergences into congruently polarized cooperative monads through the imperative and iterative application of incisor-bounced currying. As simple as that sounds, the implementation is surprisingly nuanced, so I would actually recommend the installation of one of many available libraries, many of which feature expanded syntactic extensions to make using the Dable pattern as expressive and concise as implementing a Fourier-driven comb filter over a multispectral microjoule fiber optic Ethernet interface. Okay, so let's go back to the slides for a minute. As I mentioned, this is not a terribly new pattern. And one of my favorite applications to date is, as you probably guessed, on the Saturn V rocket. Here's a picture of the IBM manufactured instrumentation unit with the dedicated Dable module highlighted here in red. And if you think about it, it makes a lot of sense that engineers would have reached for a Dable here in this application because this rocket had so many different things with mind-bogglingly complex behavioral interactions among fairly related things to think about and keep track of. The Dable module that they used here was experimental, but they found it to be extremely effective, and they figure it cut a few $1 million off of the price of the launch of a Saturn V just based on the way it was able to manage all of that complexity. Interestingly, also, on the instrumentation ring, you can probably see one of the first effective deployments of a containerized architecture with all these different panels here. So that's also kind of cool. Okay, the last thing I want to note is that while libraries supporting the Dable pattern are available on most common platforms, be aware the best possible performance will be achieved on hardware with the MMX, MMD, PhD, or DDS x86-64 extensions if you're on x86-64. Or if you're in the ARM world, you're going to want to look for something with a Cortex L77V or higher, or a F3M-UR if you're using the longitudinally extended gram meter processor architecture. As a general rule, most processors fabricated using the prefamulated Amulite process will have the necessary hardware support. And if your target environment is less modern, some software emulation is included as a fallback option in most distributions. But don't forget that you can always add first-class support with the external resistorized transwarp dongle, which you can get right now in a USB 3.2.1.0 interface. And we're expecting support for Thunderclap, MSATA, and ISA coming soon. So that's the end of my slides. That's about all I have to say. I really hope that cleared things up for you on how to use the Dable pattern.